Welcome everyone to another OGRA webinar. We are fortunate today to have Corrugated Steel Pipe Institute and Queen's University here with us to present on optimizing your budget with rehabilitation of culverts and storm sewer. I am Amin Meneda and I will be your host and moderator. I am the coordinator of technical products and research at the OGRA and the member services coordinator at the MEA. Before we go ahead and start, there's some housekeeping items. We encourage you to ask questions throughout the webinar via the Q&A function that can be found either at the bottom or at the top of your screen when you hover your mouse. So you can type a question at any time during the webinar. We will hopefully answer it during the webinar. And if at the end we didn't have enough time to answer all the questions, we will forward the questions to the presenters and they will be able to follow up with answers through email. Also, this webinar is going to be recorded and will be shared on our YouTube channel. It is now my pleasure to introduce Ray Welcock, Executive Director of the Corrugated Steel Pipe Institute. He holds a science diploma from Champlain College in 1978 and a Bachelor of Commerce from Concordia University in 1982. Over the past 3 decades, he held a number of senior executive positions at several corporations in the infrastructure industry. We also have with us today Robert Cichocki. He is a PhD student working with Dr. Ian Moore. His research topic is focused on experimentally and numerically investigating the mechanical behavior of corrugated steel structure rehabilitated with cured in place pipes. Throughout his research, Robert worked closely with industry partners, investigating the current condition of corrugated steel bridges in Ontario and possible rehabilitation opportunities. In the industry, Robert is aiming to bring insights into mechanical behavior of trenchless rehabilitation techniques so that designers and stakeholders may have a comprehensive understanding of their products and design. Now I would like to turn it over to Ray. Ray, the floor is yours.
Thank you, Amin, and welcome to each and every one of you. Hopefully you can all see my screen. It should read the CSPI, Corrugated Steel Pipe Institute, Rehabilitation of Culverts and Storm Sewers. Just to let you know, we are celebrating our 60th anniversary. The CSPI started in 1961. What we're going to cover today is I'm just going to go through a couple of minutes on the CSPI and who we are, and then I'm going to turn the presentation over to Robert, who's going to talk about the condition of Ontario structures, types of deterioration, rehabilitation approaches. And then I'm going to come back on for the last 10 minutes or so and just give you an idea of some of the work that I was involved in back in the early 2000s in the city of Windsor, and also the MTO at the 401, 410, 403 interchange, and then just give a one-slide recap. The Corrugated Steel Pipe Institute, as I mentioned, has been around for quite some time, and we represent the members of Corrugated Steel Pipe and Structural Plate Corrugated Steel. Armtech and Atlantic Industries are both nationwide players with plants pretty well in every province right across Canada, and Hubcap and Frontier are regional players. We also have, as in our membership list, ArcelorMittal, Dofasco out of Hamilton. They are the largest steel producer in the entire world with over 60 plants worldwide. We have Ironside, who make machines, Leland Industries, who make nuts and bolts, Advanced Coil Industries and Warner Custom Coatings, they do coatings, and then AK Steel is a very large steel producer of both galvanized and aluminized material. We also have members outside of Canada like Valfilm in Brazil, 2xO in Paris, France, Rondell and CMP in Australia, Viacon in Poland, Marmac is out of South Carolina, and Birkenhoek is in the Netherlands. And the reason why they want to be members of the Corrugated Steel Pipe Institute is the research and the technical knowledge that we have that we provide to them on an ongoing basis. So with that, I'm going to stop sharing my screen and pass it over to Robert.
Okay. Share screen to share. Let's post on. Okay. Good afternoon, everyone. Thanks for the introduction, Ray. So, how much deterioration is too much deterioration? How should we be designing our rehabilitations? And what are the critical components that make our design safe and effective? Well, I may not have all the exact answers to those questions yet, but back in 2016, these were some of the things that are going to steer the direction of my learning and my research for the next 5 years. So about 5 years ago, I joined Ian Moore's team at Queen's University and started on tackling these issues we face in deterioration and rehabilitation. As you can see here in the picture, I've been working on designing and running experiments on closed fit liner systems like cured in place pipe. Further, thanks to the Corrugated Steel Pipe Institute and my tax, I was able to research the current condition of Ontario's corrugated steel bridges and study a variety of rehabilitation methods for them. And what I found is that there's a lot to untangle from a lot of different resources. During my research, I reviewed a lot of resources from the MTOs, other departments of transportation, the Federal Highway Administration Program, National Cooperative Highway Research Program, different conference papers, journal articles, and manufacturers' brochures, as well as other documents on top of that. And for my investigation into these resources, I built a 3-part report that looked at what is the current condition of these structures, why are they in this condition, and what can we do about it? So in this presentation, I'm going to briefly discuss the current condition of corrugated steel structures in Ontario. Under the commonly experienced deterioration mechanisms such as corrosion, abrasion, and soil erosion, and what we can do about it. So some spot repair methods, as well as conduit relines and soil stabilization. Which for most of these things are actually also discussed in our research paper that we published on this topic. Okay, taking a look at the condition of these structures. Every bridge structure in Ontario that's managed by the MTO has to be inspected on a biannual basis. Each bridge is inspected following primarily visual element by element inspection. Out of all the bridges that the MTO overlooks, there's about 280 of them that are made from corrugated steel materials. For corrugated steel structures, the condition of the steel conduit is judged by the amount of corrosion, local and global deformation, as well as bolt cracking. So again, we're looking at pretty much a rating scale that goes from excellent condition, where there's no observed material defects, good condition, fair condition, and poor condition, where we're pretty much evaluating how much global and local deformation the corrugated steel pipe has, as well as how severe are the bolt cracks and how severe is the corrosion. And then a condition rating is sort of assigned to the element based off of what's found. So based on the condition of the elements at the time of inspection, essentially the structure is going to be given some sort of remaining value. And then that remaining value of the structure is compared to what the original value of the structure would have been if it was in excellent condition. And then we multiply that proportion by 100 to get our bridge condition index. Generally, the bridge condition index is used to prioritize the rehabilitation of bridge structures. For bridge structures that score over 70, there's no rehabilitation plan. So you can see that there's a majority proportion of bridges in this area. Between 60 to 70, rehabilitation should be undertaken within the next 5 years. And then under 60, there should be some sort of immediate rehabilitation plan. So what we're looking at in this chart is cumulative population distribution curves. And each curve represents a different type of bridge material. So For each bridge material, that curve shows what proportion of that bridge's material has at least a certain BCI value. So we're looking at the bridge condition index in the x-axis here and the proportion of bridges in the vertical axis. Taking a look at the dark red line, which represents corrugated steel, we can compare the condition of corrugated steel to other bridge populations. Looking at corrugated steel structures, we see that it has the highest proportion of bridges that are going to require some sort of immediate attention, as well as the highest proportion of bridges that's going to require rehabilitation within the next 5 years. So this had me wondering, why is that really the case? Why do we see so many corrugated steel structures that have these high proportions of structures that are going to need some sort of rehabilitation? Well, the next thing that I found when I was looking at the statistics provided from the data from the MTO was that corrugated steel structures are one of the least rehabilitated structures managed by the MTO. So here we're going to look at a similar kind of case where we're looking at the proportion of bridges that were rehabilitated across the age of the bridge. So in the bottom axis, we're looking at what year the bridges were built by and the proportion of bridges that have been rehabilitated for that age group. For corrugated steel, we see that almost for across all ages, that corrugated steel structures have the smallest population of rehabilitated structures. So cumulatively, only 37% of corrugated steel structures have been rehabilitated, while 45 to 84% of other bridge structures have had some sort of rehabilitation performed. Which brings up the next thing that I found. Historically, there hasn't been many comprehensive resources providing guidance on how to rehabilitate these structures and what the performance of these rehabilitations are, which sort of explains why we find ourselves in the position we are today. Although as of 2019, the MTO has published their own trenchless design guideline on their webpage. This guideline also provides information on many of the technologies I'll be discussing today. So all structures deteriorate over time, and it's good practice to understand how and why. So what's the problem? Why is it happening? What area is affected? And what are the signs of distress and structural concerns? For corrugated steel structures, we identified, we identified a number of root problems which consist of corrosion, abrasion, construction issues, differential settlement, and soil erosion. So today I'll be mostly discussing deterioration and rehabilitation revolving around corrosion and abrasion, as well as soil erosion. For each root problem, there's a mechanism that causes it, as well as an area that is affected and a resulting structural concern. As corrosion is a naturally occurring process, we should all be pretty familiar with it. For corrosion to occur, 4 main components are involved. First, there's the reduction of the metal by the release of an iron atom at an anodic site. So we can see our metal being reduced as an iron atom loses its electron and is being released into our solution at the anodic site. Next, we need a polar solvent for the iron atom to dissolve into where the reaction occurs. Then we need the deposition of rust at a cathodic site. So the iron atom reacts with the oxygen molecule and iron oxide is deposited on the surface of the material. And we also need a conductor allowing the flow of electrons to go between from the anodic site to the cathodic site. So when the iron is deposited as iron oxide on the surface of the material, it can regain its electron. So the metal acts as a conductor between the two sites and allows the iron to regain its electron. So corrosion is a pretty extensively studied phenomenon, as it negatively adverse is billions of dollars of infrastructure. Generally, we're okay with some amount of corrosion occurring, so long as we properly accounted for in our design life. It's well understood that the rate of corrosion varies with site characteristics, such as water acidity, so what is the pH level, water hardness, so how much calcium carbonate is dissolved in the water, resistivity, so what's the resistivity of the water, and the presence of chlorides. So Often chlorides are presented in the water or the electrolyte through de-icing salts or from the presence of seawater. Essentially, chlorides contribute a soluble ions to the electrolyte, so water is able to conduct the electricity more freely, which decreases its resistivity and increases the rate of corrosion. So the Corrugated Steel Pipe Institute keeps up to date with how to monitor these site characteristics and outlines how to pick materials that should be adequate for the design service life based off of them. So these charts are from the performance guideline for corrugated steel culverts, which is published in the technical bulletin by CSPI. As we can see, polymer coated laminated products have the best resistance to corrosion across all sorts of site characteristics. And this is mainly because the polymer acts as a barrier between the iron, which is a part of the structure material, and the corrosive environment, such as the polar solvent and oxygen. So it completely stops the reaction from being able to happen. Abrasion is an erosive process which reduces our structure's wall thickness as water and sediments flow within the conduit and through it. Generally, the sediments carried by the flow of water are called bed load. And how abrasive an environment is generally is governed by the flow velocity and what is being carried in the bed load. So here I pulled together some few pictures from Caltrans and Ohio State Departments of Transportation that characterize different water flows to their abrasive environments. So for level 1 and level 2, generally we see how low flow rates under 2.4 meters per second. And the bed load consists of carrying either kind of silty materials, clays, sand, or gravel. Once we jump up to abrasion levels 3 and 4, we're looking at flow rates up to 3.7 meters per second with moderate types of bed load volumes of angular sands, gravels, cobbles, and rocks. So, and at higher levels, we're dealing with fast flowing waters up to 6 meters per second that carry heavy bed loads. So angular sands, gravel, and rock. The Corrugated Steel Pipe Institute also has its own characteristics for abrasion levels and also recommends different materials for them again. But again, it's just basically based off of what type of material you have being carried by the water and what the anticipated flow rate is. So again, polymer laminated materials are one of the most abrasion resistant materials that we have. Further, if you're looking at really abrasive environments, you probably want to consider adding sacrificial pavements or building an open bottom structure. Next, we have soil erosion. Generally, for piping, we're concerned with water that's flowing around the structure. For piping to occur, we need some sort of permeable material for the water to flow through and water pressure to push it through. As water flows through the soil, the flow concentrates at paths of least resistance, which can occur on the outer boundary of the pipe. So in some cases, as seen in the first picture, this results in fine particles being washed away and leaving behind empty voids. In other cases, as seen in the second picture, this can progressively get very aggressive and leave large voids underneath the structure. This causes particularly large risk as the structure is losing its soil support. And from this point on, we can probably expect large settlements to occur, as well as surface depressions and potentially a sinkhole to follow. Another thing to note is that if you have high enough water pressures for piping to occur, you could also be looking at issues with the hydraulic capacity of the structure, as well as issues with the head wall and inlet of the structure. Another soil erosion process commonly observed is infiltration. In this case, we're concerned about water flowing from the embankment into the structure through some sort of unwanted leaks. Commonly observed infiltration points are joint openings, as well as perforated sections that can occur from corrosion and abrasion. In this case, voids generally develop adjacent to the structure and can extend upwards to the surface. From this point on, we'd probably expect that our conduit can experience some sort of shape distortions, surface depressions, and potentially leave a sinkhole. Further, we've also studied under simulated vehicle loads, what the effect of erosion voids are around different types of structures at a facility at Queens. Generally, what we saw is that when we have erosion voids around our structures, they amplify the section forces in moments. so they reduce the capacity of the structure. So here's a chart summarizing what I learned about how abrasion and corrosion can cause structural distress and concerns. Generally, abrasion and corrosion will result in the loss of wall thickness, as well as perforations, and lead to diminished structural properties. When we apply our vehicle loads and gravity loads, we can probably expect some sort of cross-section shape distortions and potentially collapse. And if that wasn't worse enough, section loss and perforation also leads to openings facilitating soil erosion. So we also open up an opportunity for another deterioration mechanism to occur. So here we have another chart summarizing what I learned about soil erosion and structural distress and concern that it causes. Once we have a means for soil erosion to occur, either piping or infiltration, voids can develop and diminish the structural support the soil has to offer. With our given gravity and vehicle loads, we can kind of expect different barrel and soil movements to occur, barrel misalignments, cross-section and shape distortions, as well as surface settlements and sinkholes. Further, these types of distortions and movements can also cause separated joints, which also leads to more opportunities for soil erosion to occur. When it comes to rehabilitation, there are a couple of newer publicly available published resources which discuss the variety of technologies available. So first, we have a document coming from the National Cooperative Highway Research Program called Culvert Rehabilitation to Maximize Service Life while Minimizing Direct Costs and Traffic Distributions. This document discusses a variety of methods and applications. Specifically, it gives information about what these methods involve, as well as some of their limitations and advantages. Further, it also tries to provide guidance on choosing an appropriate rehabilitation method with the use of flowcharts. Second, we have a recently published document from the MTO under the MTO trenchless design guideline. This document tries to provide the best, honest, and up-to-date guidance for a variety of rehabilitation methods. With this document, the MTO kind of tries to come up with a standardized approach for design, which also considers the most up-to-date scientific findings, as well as industry standards. So this is a really great resource once you kind of have a rehabilitation technique in mind, because it does provide information about all the different aspects of design, reaching from environmental, hydraulic, as well as structural considerations. But picking the right technology to rehabilitate can also be tricky. Some of the common resources I've reviewed and some come across that try to tackle this problem are the Culvert Rehabilitation Manual, so that NCHRP project, Caltrans supplement to the Culvert Repair Practices Manual, as well as Decision Analysis Guide for Corrugated Metal Culvert Rehabilitation and Replacement using Trenchless Technology. So this NCHRP project actually offers some pretty easy to follow use flowcharts to help you evaluate which rehabilitation technology could be used in your situation. As for the other resources, they kind of offer some concise decision trees for evaluating different options, descriptions of the technologies, as well as follow-up case studies that for each type of technology being applied. So in my own research, what I tried to do is link what I learned about deterioration to rehabilitation in my own chart. In this chart, we're looking at all the possible reasons we have to be concerned about something, and we're trying to link that to a rehabilitation method. So in some cases, I found we're able to link one source of deterioration directly to a rehabilitation method. In other cases, when we're experiencing significant shape distortions, and that may no longer be the case. For example, if you're looking at loss of wall thickness and perforations, perhaps you just need a spot repair method to be applied. If you're concerned about those things along with shape distortions, perhaps you want to pick a rehabilitation method that's going to also add some stiffness to your system. If you have soil voids, you need to be grouting those soil voids. If you have bolt issues due to like improper assembly, those things can also be rebolted and repaired. Okay, so now what I'm going to do for the final part of this presentation is take a closer look at some of these rehabilitation technologies before handing it back to Ray. Specifically, we're going to look at some spot repair methods, as well as some conduit reline techniques. So Partial concreting is a popular rehabilitation method for essentially repairing damages due to corrosion and abrasion. The method's pretty commonly used by the Federal Highway Association, Caltrans, Ohio State Department, as well as other departments of transportation. Both Caltrans and the Ohio State Department of Transportation have guidance on non-structural and structural type rehabilitations that sort of just aim to restore that structural capacity of the invert after it's been corroded out. Generally, we see rehabilitations rehabilitating 90 to 180 degrees of the invert, and either conventional or high strength concretes are used. As you can see in the picture, we have L angles that are welded across the spring line of the structure, as well as a wire mesh being used for light reinforcement. So in this case, the wire mesh is actually being spot welded to the structure, where they do about a 4-inch spacing circumferentially, while about a 30-inch every 30 inches down the length of the pipe. Further, before grouting or applying the concrete invert, they also grout any voids that are present in the structure with. After the voids are filled, then the cement mortar is applied. Paved invert is one of the rehabilitation technologies that have been previously studied at our lab in Queen's University. So for this project, there's a previous master's student, Jacob Tetro, who investigated the performance of a deteriorated culvert before and after rehabilitation. So in this project, the culvert was buried at our test facility at a cover of 0.5 meters and tested under Ontario truckloads. While being buried in our test facility, the culvert was rehabilitated with a non-structural method specified by the Ohio State Department of Transportation. This rehabilitation technique generally involved having L angles welded to the bottom of the haunches of the structure, as well as wire mesh sitting on rebar chairs. After the reinforcement was put into place, the invert was cast with a Portland cement concrete that had a 7-day compressive strength of 30 MPa. So while being tested under these service loads, we saw that this installation actually increased significantly the stiffness of the system. So essentially, we saw a more stiff system after the rehabilitation. Although the concrete experienced bending, it didn't crack under this loading configuration. And ultimately, the ultimate limit state in this configuration was that the corrugated steel pipe was bending. For our next spot repair method, we have partial relining. This method is similar to the paved invert method, where we're trying to restore the structural and hydraulic integrity below the spring lines. The invert liner material is selected while also considering abrasion and site characteristics. So abrasion and corrosion site characteristics, and generally the new liner portion of the structure is assembled outside of the structure and then brought into the structure. Once inside the structure, the lower portion is bolted onto the existing section where connections have previously been welded onto the structure. For this particular system, the connections are actually designed to transfer normal and flexural forces between the new and old portions of the structure. Once everything is assembled, the concrete is then poured between the new and the old structure, and generally props are installed to compensate for any lifting forces due to buoyancy. When passage for aquatic species also becomes a critical concern, polymer-coated river fish baffle may also be applied to reline the invert of the structure. The polymer coating is laminated to the plate, which adds protection against corrosion. So these plates are installed transverse along the length of the pipe. This is so that we can build up the volume of water between the two plates. And they also have these cuts installed in them, which allow for water to flow through as well as fish to pass. Okay, next we have conduit reline techniques. Cured in place pipelining is a method in which a flexible tube material is saturated with a thermosetting resin. This saturated tube of material is then expanded into a deteriorated structure using air pressure. Generally, there's two types of CIPP liners or cured in place pipe liners being installed. We have the conventional felt liner, which is typically just heat cured. And the second liner we have is the UV cured liner, which is a reinforced liner. The UV cured liner system uses reinforcing glass fiber polymers to achieve a much higher stiffness properties than we could ever achieve with the conventional liner system. So if we're looking at the fiberglass liner and its elastic modulus, it has about an over magnitude higher stiffness than the felt liner, but still about a magnitude less than than corrugated steel itself. Typically, these liners are installed in diameters from 100 millimeters to 1800 millimeters. So at Queen's, as part of my research project, I was actually fortunate enough to be able to witness these two types of liners being installed, as well as conduct an experimental investigation on both of them. Here I have a short video just of the liner being installed using the inversion method at our testing facility. As you saw in the video, the liner is made up of felt material, which is also saturated with a thermoset resin. Once the slot liner is put into the installation rig, it's blown up using air pressure. After it's inverted, the steam is turned on, and then the resin is cured solid. So guidance for these installations, design methods, and quality assurance for this project is provided by ASTM F1216. Next, we can see a liner being installed using the pulled in place method and being cured with UV light. So with this installation, the liner is pulled into place while being dragged over a sliding sheet. Once it's in place, it's expanded with air pressure, and the UV light train is then inserted and the liner is cured. Guidance for the installation, design, and quality assurance for GFRP liners is provided by ASTM F2019. So CIPP liners
came in, Robert, sorry to interrupt.
Yeah.
Regarding the grouting for, I guess, sensitive species. Question came in asking, do you need a permit for the grouting because of sensitive species or any environmental issues?
That's a great question. So I'm not 100% sure about the environmental considerations for grouting. If I had to start looking to get an answer for that, I know that the MTO trenchless design guidelines talk about grout in place liners, and they do talk about environmental concerns. So that'd be my first place to look into that, to see if there are environmentally friendly grout types, as well as if there's anything locally available that could provide a solution that meets environmental considerations.
I see. And another question, I believe it was regarding the relining.
Mm-hmm.
Does it affect the capacity, or how does it affect the capacity? Do you need to redesign or consider?
Yeah, so for like an entire conduit reline system, some of the research, so this kind of just goes right into what some of the research I've been doing right now and the findings we've had. We're looking at studying how this, especially cured in place pipeliners, how they affect the capacity of these structures. And one of the things that we found is that it does actually add additional stiffness to the system. And, but it doesn't really follow the design guide. The behavior of the structure didn't really follow the design guidelines that we saw from the ASTM F1216 standard. So again, we're kind of looking at like a special case where we have this irregular geometry and we're looking at the stiffness of the system. So we saw kind of like a different behavior that occurs where we have bending across the top of the crown and the liner sort of behaves as an arch, as opposed to what the ASTM F1216 standard kind of calls for you to design these liners against. So I'm just gonna, unless there's more questions, I'm probably just gonna talk about these couple points here, and then I'm gonna segue and talk a little bit more about the design considerations for these liner types.
Sure, go ahead. Thanks.
Yeah, so there was one retrospective study that looked at CIPP liners where they went into insight investigations. And from their research, what they found is typically that these liners are probably going to be exceeding their 50-year expected design life. And then another cool fact that I found about these liners while reading about them is that as of 2010, there's 64,000 kilometers of length of liner that have been installed. Okay, so for structural design, typically we're looking at hydraulic pressures acting on the outside of the liner. And historically, it's been designed using the enhancement factored method. And for surface loading, the liner also has to be designed to be able to withstand direct bury using a fiberglass pipe design equation. So this fiberglass pipe design equation is actually pretty dated and considers like a buckling failure mechanism, which we didn't really see in our research at all to govern the behavior of the pipe. So previously, a lot more research has been performed over the last couple of decades where more comprehensive theories for hydrostatic pressures have been developed. So we're able to design liners in more complex configurations, such as like the pipe arch culvert that I'm studying right now. Although one of the issues that we're still trying to tackle is how to design close fit liners against surface loads. Currently, there's a couple ongoing projects being undertaken to update the guidelines for these liners. First off, we have the ASCE project, which is going to come up with guidance for a close fit lining design. And then next, there's also an NCHRP project, which is being undertaken to come up with a load reduction factor design for CIPP liners. So out of the study for this one, hopefully this should be more relevant guidance coming against for designing against surface loads. So I kind of hope that wraps up answering the question that we had previously.
Yes, and there are some more questions that came in. So do felt liners reestablish any loss of ring compression strength to the host pipe, which may have been lost?
Yeah, so that's a good question. From what I've seen in research, like if we just go back to looking at comparing the structural properties, so like what's the cross-sectional area, like the thrust stiffness of like the EA of the corrugated steel pipe versus the felt liner. If you multiply these two numbers together, you're going to probably get a number that's about 5 times less than what the stiffness of the corrugated steel pipe would be. That being said, thrust doesn't always govern the design of this system. So there's also since they're flexible pipes, there is a soil structure interaction that is going on. And we're still kind of looking at evaluating, coming up with a load reduction factor design where we're evaluating thrusts as well as bending.
I see. Also, another question is asking, is GFRP lining a suitable method to be applied for in situ rehabilitation? What are your thoughts?
Yeah, as a first thought. So I know I think so long as everything, you can follow all of your design guidelines with regards to environmental and structural and hydraulic considerations. I think we're also going to be seeing better guidances coming forth with regards to the design of these liners. So I do think it's going to be a good method, assuming that you can meet all your design criteria.
Okay, we have a few more questions, but I guess I'll let you finish, or if you're finished, we can pass it over to Ray, and then we'll take the rest of the questions at the end.
Yeah. Okay. So I guess so we're at my 30-minute portion here. I'll probably take 5 more minutes to kind of just jump through a couple more slides that I have, and then I'm happy to take more questions on after the presentation or after my portion is complete. So another common rehabilitation technique is grouted slip liners. Grouted slip lining is a rehabilitation technique where sections or segments of pipe are pushed into the old deteriorated pipe. So as we can see in this picture, it consists of a smaller diameter pipe that's going to be inserted into a larger diameter pipe. And generally there's a gap left between the two pipes, which is grouted with either a low strength or a high strength concrete. These methods can be applied in structures from 0.3 to 3 meters in diameter, as well as much larger structures as well that exceed 3 meters diameter. One of the things that's neat about this structure is the versatility of the materials that can be used. We can use thermoplastic pipes, reinforced concrete, centrifugally cast, FRP, as well as corrugated steel materials. So I'm not going to get into this slide too much more just because we are kind of running short on time. But this is one of the technologies we did study in our lab. And then you can follow up looking more at the results of what we found. Essentially, it does provide a great additional stiffness to the system. And we also were kind of curious as to what the effects of grout choice were when we're studying the grout in place liner. And we kind of found two significant varying behaviors. So if you're interested in that, the MTO Trenches Design Guide also talks about these systems, as well as we do have published research which investigates this behavior. Spiral round lining is another technology that is possible to use. Essentially, what spiral wound liners consist of is winding a continuous strip into a liner and inserting it directly into the deteriorated pipe. As a liner is wound into the pipe using a specialized machine, the edges interlock to form a continuous watertight liner. So these edges are kind of manufactured with male as well as female joint edges that can either be chemically, mechanically, or thermally joined. Also, different PVC and high density polyethylene composites or non-composite strips can be used to achieve different liner stiffnesses. When it comes to installation, generally there's kind of two types: this loose fit where you have a fixed diameter, and then this kind of becomes a grouted slip liner because afterwards you have to grout the space in between the liner and the spirally round line and the existing pipe. In the second one, we have this kind of close fit liner where we install it at one diameter and then it expands to fit the other conduit after it's been pushed in, after it's been installed and pushed through the pipe. One more technology that we looked at, especially we studied this one in our research facility as well and published literature about it, is, sprayed on cementitious liners. So generally this method creates a concrete liner within the existing pipe. Typically the lining is pumped in at high velocities while a rotating head centrifugally casts the motor onto the pipe. While the head spins, the machine runs back and forth through the pipe until the desired thickness is reached. Following the similar set of experience that I previously talked about, where we're looking at these Ontario truckloads at these shallowest Culverts, we saw that this rehabilitation method did demonstrate to significantly stiffen the system. Further, we also saw that it kind of behaves as like either a rigid or a semi-rigid pipe. And we were also able to propose a variety of design equations for this method using either composite or non-composite action. So what we looked at today is the current deterioration mechanisms of corrugated steel pipe, as well as typical signs of distress and rehabilitation opportunities. So I kind of just built a chart kind of looking at my learning, going from, well, what is the root problem of these structures? How is it occurring? Why am I concerned? And then what are my opportunities for fixing it? So now I'm going to hand it back to Ray, where he can briefly talk about a case study, or I can also take this opportunity to answer a couple questions.
Thank you, Robert. We can turn it over to Ray, and so that we'll take the questions at the end then, to make sure we cover the topics on the agenda first. The floor is yours, Ray.
Thank you, Amen. Can you hear me okay?
Yep.
Okay. First one I wanted to talk about is just a couple of relines that I was involved in back in the early 2000s. First one is a Windsor reline, Ontario reline. The built date was 1975. It's at the location, the corner of EC Row Express and Howard Avenue. And it was basically downstream from a junkyard. So very, very corrosive water passing through that particular storm sewer. The pipe was an 1800 millimeter diameter galvanized CSP. The gauge was 1.6 millimeters and the length was about 100 meters. And here's an overshot picture of where that storm sewer was. So it more or less basically underneath the EC Row Express Highway, there's a Howard Avenue going underneath. And it started just where that Starbucks takeout is, and then went all the way out to that outlet that you can see across there. Here's a picture of the upstream. It's hard to tell, but that was very corrosive water. You're probably talking about 500 parts per million with regards to chloride, so not very pleasant. And there is the downstream, the outlet. So the reline date that we were called into was about 2005. So the pipe was about 30 years old. And what we did was we relined it with a 1,500 millimeter diameter polymer laminated spiral rib pipe. Spiral rib pipe has a Manning's N of 0.012. So you're talking about a smooth wall pipe ribbed on the outside. The things we had to do were drain the water, clear the debris. We used cofferdams and pumps, and ensuring all environmental regulations were met. Here's a schematic of a small diameter reline showing the coupling, sliding, and just blocking details. But I'm gonna move forward here and keep going. So you insert the first section down, through the pipe. You set it to the line and grade using adjusting rods on both ends. So you basically see the new structure inside the old structure with an end view. You block the first section, so from the top and the bottom. You place the next section up against the first section there. You block the tail end of that second section. And then what we did was we placed internal and expanding band gaskets on the inside. And here's a picture of just what an internal expanding band looks like. So that would basically be going right around the inside of the pipe. You repeat that until all the sections are installed. You install the bracing to prevent flotation during grouting, as you can see there in that vertical bracing. And then you grout in stages. So we did a first lift, we did a second lift, and then we did a third lift. And you can see the grout ports there on that particular picture with a vertical brace down the center. I was down there in 2017. I wanted to inspect it. The pH was 6.0. The water, the chlorides at that time were 363 parts per million. So polymer laminated was the right material. What I did was I took a Scotch-Brite pad and I just wiped off some of the dirt and so forth. And I checked it with my positector down around the invert just to see what it was. And it came up about 13.5 mil, which the coating of a polymer laminated pipe is anywhere between a minimum of 10 up to 13, 14. So that pipe was in excellent shape, but you can see some of the stuff that's lying in the bottom, the rocks that could cause some abrasion and also the very corrosive water. The last one that I wanted to show was the 401, 410, and 403. This was an Ontario reline. The built date originally of this particular was in 1974. The location, as I mentioned, intersection of those three major highways. There was, at the time, there was an average of 320,000 vehicles per day going over that particular structure. The existing pipe was a 30-50 millimeter reinforced concrete pipe, storm sewer. The length was about 200 meters. The culprit was the road salt from up above. And you can see the owner was MTO, the consultant Morrison Hirschfield, the contractor was Underground Services. Replacing that storm sewer was not an option given the impact on transportation, commerce, and obviously public opinion. There's a picture of from the top, just looking down at the Highway 401 eastbound and westbound lanes with the 410 heading north and then the 403 off to the side there. That red line, as you can see with the arrow, is the storm sewer pipe. So it started in the northwest corner and basically ended in the southern part and into an industrial section. Here's a picture back in 2003 of the concrete storm sewer. The salt had basically leached down from up above, obviously perforated, got into the rebar, and started cracking and corroding and so forth. So we were called in. We relined it in 2004. We used a 2850 millimeter galvanized corrugated steel pipe. We used coal tar epoxy coating on the invert. It was a 125 by 25 profile with a 4.2 millimeter thickness. And we used composite drainage fabric was installed outside the CSP at joint connections. The challenge was installation because there was a damaged section. The damaged section of the RCP was over 150 meters from the outlet under the main travel portion of the 401. So we had to fabricate the CSP in 3.15 meter lengths to negotiate the bends in the existing sewer. And we used internal couplers as I showed before. Because again, I just wanted to show you there was a bend there. So we had to, when those CSP pipes were being pushed through, we had to get them around that bend. And it was very tricky and very difficult. So we went with smaller pieces of pipe because normally corrugated steel pipe goes anywhere from 6 meters to 9 meters in length and even longer than that. But nevertheless, standards are 6 or 9 meters. There's a picture of a forklift truck with a carrying frame that was used to put those in place, and then they were pushed along and, you know, till they butted up against each other, and then internal coupling systems were used, and then grouting took place between the old and the new. There's just another picture with CSP with the screw jacks and the grout plugs that were in play, 3.15 meters in length. The whole job took about 3 months. It was planned over a 2-winter period, which was 6 months, but basically it was completed in 3 months. So they didn't have to, you know, it was a great savings to the MTO. And obviously they didn't have to call back the crews the following winter to finish it off. And last slide that I wanted to show is that if you're ever looking for reline procedures with regards to small pipes or larger pipes, on our website at www.cspi.ca, we have procedures for small diameter and also a large diameter, and linkages to Robert's research that he has done on behalf of us. So that's it. So I'll turn it back to you, Amin.
Thank you, Ray. Yeah, so we will start with where we left off with questions. Okay, I guess it's a question for Robert. Have HDPE slip liners been compared to any of the other methods?
So as far as I know, nobody at our facility or research group has compared the performance of different rehabilitation technologies. But what we have done is we have looked at HDPE slip liners specifically and seen how they perform. So how like a deteriorated corrugated steel pipe would perform before and after rehabilitation.
I see. And another question also for you. Has your research looked at the cost of various rehab alternatives and how they may affect an owner or consultant's rehabilitation decision? So basically,
yeah,
so life cycle.
One of the things I was looking at for the presentation title is does say optimize costs, and I was thinking to myself, I'm like, well, I'm more of a structural side of everything, so I'm not covering any life cycle analysis or cost analysis for these things.
I see. I guess maybe I'll see if Ray, do you have any comments regarding that question? Is there any resources for cost of various rehabilitation alternatives and how they may affect the owner's decision?
Yeah, I think it's all relevant to each particular site. You know, there's probably no one right answer when it's all said and done. There are so many different methods that one can undertake. I believe it's a matter of, you know, each one would have to be costed out, you know, for each particular project. So to say this one's less expensive than this, it's probably not a fair answer at this point in time.
Yeah, I also just think about it's like what's available locally around your region, because sometimes trying to get some of these technologies out to where you are isn't necessarily feasible for the contractors. But if you're looking at evaluating different options for rehabilitation, that NCHRP project in the slides does cover a whole bunch of methods which could be applicable. So you can kind of try to imagine to yourself which one would be the most cost effective, but you should still do your own due diligence and reach out to contractors and see how much it would cost to get that project done.
And if I could add that if it's just the invert alone and you're trying to rehabilitate the invert, doing the invert versus doing the entire peripheral obviously is going to be a lot less costly, you know.
I see. Thank you. Again, for you, Ray, regarding the rehab options that you mentioned, that you speak about in the case studies, what are the typical diameters that are suitable for these kind of rehabilitation?
Well, you could, yeah.
The person who asked mentioned that the small diameters is his concern.
You could probably start, you know, I mean, it's a tough question. As long as you don't have deformation in the hose pipe or whatever, and as long as you can, you know, push and you know, you can use skids, you can grease them or whatever, and as long as you can push things through the hose pipe, you know, they could be as small as 300 millimeter, you know, or for us, it would be 450 millimeter, particularly using spiral rib pipe, because you're talking about a smooth wall and much thinner with regards to the corrugation. So, you know, these things can be joined outside also, not only, I mean, the two that I showed were joined inside using the expanding couplers, but you could join these outside and push them all the way through to, you know, to the outlet, so to speak. So, yeah, you can go pretty small, provided you're able to, you know, push them through to the other side, and there's no deformation of the hose pipe.
Thank you. There's another question also for you, Ray. Also regarding the case studies, specifically for the long culverts, do they have any maintenance holes in between?
I don't understand. I saw that question, but I don't think I understood what it was referring to. You know, when you're putting these together, obviously you're securing everything up and you're filling the voids, you're grouting in between the old and the new, you're putting in gaskets, you know, you're making sure that they're basically watertight. So I'm not sure what the maintenance holes they're referring to, what that actually means. You know, I didn't understand the question. Maybe they could re-elaborate or change it, and you know, I could come back at it.
Okay. We're almost at time here, but we have some room for more questions. Robert, for you, can you comment briefly on where high stresses versus low strength in relines?
Sorry, could you say that one more time?
Can you comment briefly on where the high stress versus the low strength exist in the reliners, or where the weak points and where the strengths are?
Oh yeah, so could Robert comment briefly on where high stresses versus low strength in relines? Okay, so I'm gonna guess that we're talking about low strength and high strength rehabilitations probably. One of the things is that a lot of these methods, especially like grout in place liners, they're gonna add stiffness to your pipe. So essentially, same with like the cement mortar liner, essentially you're gonna be converting a pipe from like a flexible pipe to maybe a semi-rigid pipe to possibly a rigid pipe. And then that kind of depends on what you wanna do in your like what you wanna do in your conduit. So from my own opinion, speaking from nowhere else from that, I think like depending on how much shape distortions you have, you might be considering, oh, maybe I want like a high strength conduit reline versus like a flexible reline, which would be achieved with like a spirally wound liner or possibly a low strength cured in place pipe liner.
I see.
So I hope that covers the that question.
I think so. If the person who asked it feels that they need more elaboration, they can feel free to post another question on as a follow-up. Regarding the previous question, Ray, the person elaborated maintenance holes. They mean manholes by that.
Oh, okay, good question. I don't believe there were any on that particular storm sewer. I may be corrected on that, but as far as I know, you could enter those pipes from either the inlet or the outlet, and I do not believe there was any manholes in place. I may be wrong, but I don't remember. I could find that out though for that particular individual. I could find that out.
Okay. So I would like to ask for the person who asked the question. I see that he asked it or she asked it anonymously. If you can post your question without checking the box for anonymous, we can follow up and see your email and follow up with you. There's a few more questions that came in. We'll take a couple of more questions, and we'll end the webinar then. And for the rest of the questions, we'll follow up after. Someone is asking, what is for Robert, what is the strength of the grout used for the relined rehab test?
I'd have to look that back up.
Okay. And what?
So actually, sorry. So for the grout reline tests, there was low strength grout concrete, which I can't remember what the compressive strength was, and there's a high strength grout concrete, and both the methods were compared. If you want to look more into it, then that research is published, and as well as that MTO trenchless design guideline does comment and reference that as well.
I see. The last question we're going to take, someone is asking, is there a way to determine the host pipe deformation if the host pipe is submerged and is in submerged condition without having to perform dewatering operations?
I'm not sure I understand, but I also don't think I'm going to be able to answer that.
So Ray, do you think there's any methods to determine the deformation or the significance of the deformation in a host pipe without having to do a dewatering operations? Can you use ground penetrating radar, any other technologies to do that?
There may be, like using somebody like Inversa, it's quite possible. I've never been involved, I guess, in a particular case like that. Most of the structures or projects that I've been involved in, one could actually enter and get inside and, see what was going on rather than, I guess it depends on how full we're talking about. I guess you could take a canoe through there if it's big enough, it's hard to say.
Mm-hmm.
That's a tough one. I mean, there may be, like I say, there may be systems out there at this stage of the game that I'm just not aware of.
All right. Well, with this question, we would like to end our webinar today. And thank you very much, Ray Wilcock and Robert Cichocki, for presenting today and sharing your valuable experience and knowledge with our attendees. And to everyone, the webinar will be recorded and will be posted on our YouTube channel. The rest of the questions will be sent to the presenters to follow up with you guys with answers. And with that, thank you all so much for attending, and thanks again, Ray and Robert, for presenting.
Thank you, Amanda.
Thank you.